Ever wondered how atoms know how to arrange themselves into molecules? Today, we're unveiling this atomic mystery. The secret lies in a tongue-twisting concept known as the valence shell electron pair repulsion theory, or VSEPR theory for short. This theory is the key to understanding the architecture of the atomic world, the shapes and structures of molecules. The VSEPR theory was developed to predict the shapes of molecules, a task that might seem simple, but in the world of atoms and electrons, it's anything but. Picture this. You're an electron in the outermost shell of an atom, the valence shell. Now, electrons are negatively charged, and just like how two north poles of magnets repel each other, these electrons also want to stay as far apart as possible. This idea of electron repulsion is the cornerstone of the VSEPR theory. But why is this theory so important, you ask? Well, the shape of a molecule often determines its properties. Whether a molecule smells sweet or sour, whether it reacts violently or not at all, or whether it's a gas, liquid, or solid at room temperature, it all comes down to its shape. And to predict that shape, we turn to the VSEPR theory. Imagine a world where we didn't understand the shapes of molecules. We wouldn't know why water is liquid or why diamonds are hard. We wouldn't understand why soap cleans or why salt enhances flavor. The VSEPR theory is our key to unlock these mysteries. So are you ready to dive deep into this fascinating world of atoms and molecules? Buckle up, because it's going to be an exciting journey. First things first, let's understand what we're dealing with here. The world of atoms is a fascinating one, and at the heart of it all are the valence electrons. These are the electrons occupying the outermost shell of an atom, also known as the valence shell. Now, you might be wondering why these particular electrons are so significant. Well, these are the ones that take part in forming bonds with other atoms, and they play a starring role in the formation and properties of molecules. So, let's dive deeper. You see, the valence shell electron pairs are like the unsung heroes of the atomic world. They determine the shape of the molecule, not by their numbers, but by how they position themselves. And here comes the interesting part. These electron pairs are not exactly best friends. They repel each other. Yes, you heard it right. Just like magnets with similar poles, these electron pairs try to stay as far apart as possible. This behavior leads us to the crux of the valence shell electron pair repulsion theory, or VSEPR theory in short. This theory states that the shape of a molecule is determined by the repulsion between the electron pairs in the valence shell of an atom. The electron pairs arrange themselves in such a way that they minimize this repulsion, leading to the formation of molecules in specific shapes. For instance, if an atom has two electron pairs in its valence shell, they will position themselves at the opposite ends, leading to a linear shape of the molecule. But remember, the world of atoms is not as simple as it seems. While this theory does give us a basic understanding of molecular shapes, it's not the entire picture. There are other factors at play as well, but for now, let's stick with the basics. Now that we've got the basics down, let's explore how this theory works in action. Now, let's see what happens when these electrons start to interact. When it comes to the VSEPR theory, it's all about the electrons in the valence shell. They're the ones that determine the shape of a molecule. Let's take a look at two examples: water, H2O, and ammonia, NH3. First up is water, a molecule we're all quite familiar with. Water is composed of two hydrogen atoms and one oxygen atom. The oxygen atom, being the central atom, has 6 valence electrons. 2 of these electrons form bonds with the hydrogen atoms, and the remaining 4 exist as 2 lone pairs. Now, according to the VSEPR theory, these electron pairs are going to repel each other, and they'll arrange themselves in a way that places them as far apart as possible. In the case of water, this results in a bent or V-shaped molecular structure with a bond angle of approximately 104.5 degrees. Next on our list is ammonia. This molecule is made up of 1 nitrogen atom and 3 hydrogen atoms. The nitrogen atom has 5 valence electrons. 3 of these electrons form bonds with the hydrogen atoms, and the remaining 2 exist as a lone pair. Just like in water, the electron pairs in ammonia repel each other and arrange themselves as far apart as possible. This gives ammonia a trigonal pyramidal shape with a bond angle of approximately 107 degrees. Now you might be wondering, why are these bond angles not the same? Why doesn't water also have a bond angle of 107 degrees like ammonia? Well, that's where the concept of bond angles comes into play. Bond angles are determined by the repulsion between electron pairs. In general, lone pairs of electrons repel other electron pairs more strongly than bonded pairs do. This is because lone pairs are only attracted to one nucleus, while bonded pairs are attracted to two nuclei, which helps to offset some of the repulsion. In the case of water, the two lone pairs of electrons push the bonded pairs closer together, resulting in a smaller bond angle compared to ammonia, which only has one lone pair. So, in essence, the VSEPR theory tells us that the shape of a molecule and its bond angles are determined by the repulsion between electron pairs in the valence shell. The more electron pairs there are, the more they'll repel each other, and the more they'll work to keep their distance. Remember, the key to understanding the VSEPR theory is to remember that like charges repel, and electrons, being negatively charged, are no exception to this rule. They'll always try to stay as far away from each other as possible, and this behavior is what shapes our molecules and determines their properties. So just like people, electrons also like their personal space and will do anything to keep it. But just like any theory, VSEPR is not perfect. Now don't get me wrong, the valence shell electron pair repulsion theory, or VSEPR, is a fantastic tool for predicting the shape of small, simple molecules. It's like the compass of the molecular world. But as we venture into the territory of larger, more complex molecules, the compass starts to waver. You see, VSEPR is based on the idea that electron pairs in the valence shell of an atom repel each other and try to stay as far apart as possible. This makes perfect sense in a world where all molecules are small and uncomplicated. But in the real world, molecules can be like twisted labyrinths, with multiple bonds and atoms of different sizes. VSEPR, in its current form, doesn't have a way to account for the influence of the atom size. It treats all atoms as if they were the same size, like identical marbles in a jar. But atoms, like the people who study them, come in all shapes and sizes. A larger atom can have a greater influence on the shape of the molecule, something that VSEPR doesn't consider. And multiple bonds? Well, they're another story. In VSEPR's world, a single bond and a double bond are treated as one and the same. But in reality, a double bond behaves differently than a single bond. It's like comparing a solo dancer to a pair of synchronized swimmers. They move differently, they occupy space differently, and they influence the world around them differently. So does this mean we should toss VSEPR out the window? Absolutely not. Despite its limitations, VSEPR remains a powerful tool for understanding the basics of molecular shapes. It's like the foundation of a house. You can't build the rest without a solid base. So, while VSEPR theory gives us a solid starting point, it's always important to remember that in the world of chemistry, there's always more to learn. And that, my friends, is a brief journey into the world of molecular shapes. We've traversed the fascinating landscape of the valence shell electron pair repulsion theory, a cornerstone concept in chemistry. This theory is like our compass, guiding us to understand how molecules form and why they shape the way they do. In essence, it's all about the push and pull, the repulsion between electron pairs in the valence shell of an atom. Remember, like a group of people trying to maintain personal space in a crowded room, electrons, too, strive for maximum distance from one another. That's what gives molecules their unique shapes. But let's not forget, every theory has its limitations. The VSEPR theory, too, isn't a one-size-fits-all solution. It can't accurately predict the shape of all molecules, but it's a wonderful starting point in the quest to unravel the secrets of the atomic world. I hope this gives you a better understanding of the tiny atomic world around us. Remember, in chemistry and in life, it's all about finding the right balance.